This is our third example in the surface area of a curve rotated about an axis. So we'll find the surface area created. In this video specifically, we're going to rotate about the y-axis. One thing we need to recall is our surface area formula. And the surface area formula is C to D 2 pi r. That radius is going to be some x being a function of y. So we can think of it as being x or g of y. So 2 pi g of y, and then arc length, which is 1 plus the derivative of x with respect to y, that quantity squared, integrating with respect to y. Now, what we want to think about is what we're given. The function that we're given here is this curve, y equals 1/2 x squared plus 1. This is a parabola, and we're given bounds on the x-axis. X is between 0 and 1. That's our closed interval. So let's think about what this graph looks like before we even start the problem. Right? So it's a parabola shifted up 1 unit and compressed vertically by 1/2. So my curve actually looks like this, more or less, with a y-intercept at 0, 1/2. Now, we're not interested in what's occurring over here on the left side of my y-axis, because we are only interested in what's occurring between x equals 0 and x equals 1. X equals 1 gives us a point on the graph here. So we've got this point 1, and we need to know that y value. Well, remember, the function we're dealing with is y equals 1/2 times the quantity x squared plus 1. All right, so if I plugged 1 in for x, I get out the value of 1. This ordered pair is 1, 1. So what does that mean for my C and D, my bounds? Since we're going to go about the y-axis, these bounds have to be in terms of y. We have from 1/2 to 1. All right, so at that same time, y is between 1/2 and 1. Also, we need our function. Right here, what we're given is y in terms of x. We need x in terms of y. So we have to rearrange that as well. Rearranging that, I could say, well, this is 2y equals x squared plus 1, or 2y minus 1 equals x squared, and then you square root plus or minus the square root of 2y minus 1 equals x. And when we use a square root to solve, that plus or minus has to be there. But we only need half of that. We don't need, both the left and the right piece of this parabola. So we're only going to use the positive. All right? So my function that I'm dealing with, we've got x equals the square root of 2y minus 1. So I paused and cleaned my page up a little bit. We know what our C to D interval is. We know what our function x in terms of y will be. And we now need this derivative, and I like to go ahead and square it before I plug it all in. So keep in mind, this is the same as x 2y minus 1 to the 1/2. Now if I go to find the derivative of x with respect to y, I'm going to need to use the chain rule. So that's 1/2 2y minus 1 to the negative 1/2, then times the derivative of the inside, which is 2. That simplifies dx dy equals 2y minus 1 to the negative 1/2. And if we look at squaring that, dx dy quantity squared, well, squaring that, that's going to give us 2y minus 1 to the negative 1. Because if we look at squaring that, that would be negative 1/2 squared, multiply powers, you get negative 1. All right, so now that we have all of this information, let's plug it into our surface area formula. So the surface area equals, we're going to go from the integral from 1/2 to 1, 2 pi, we end up with the square root of 2y minus 1, and then I have times the square root of 1 plus, and this is 2y minus 1 to the negative 1 dy. And I encourage you to pause here, make sure you understand how we were able to determine this integral setup. Make sure it all makes sense to you. So now we're going to go about solving. 2 pi, that's going to come in front. And when we are multiplying radicals, basically we can multiply those radicands and create one big radical. So I have 2 pi, the integral from 1/2 to 1. This becomes 2y minus 1 times 1 plus 1 over 2y minus 1 dy. So this first piece, this can distribute to both of these. That's going to clean up quite nicely when I do that. So I have 2 pi, the integral from 1/2 to 1, and I end up with the square root of 2y minus 1, and when this ends up in the numerator here, we're just going to end up with a plus 1. And of course, plus 1 minus 1 are going to cancel. So the integral has become quite simple. Got the square root of 2y dy. Now, the square root of 2, using properties of integrals, that's the square root of 2 times the square root of y dy. I think I said properties of integrals, but properties of radicals. I can split this apart. This constant can come in front. All right, so this is 2 root 2 pi, integral from 1/2 to 1, and I have left under there the square root of y, or y to the 1/2 dy. So simple with our power rule. If I add 1, that gives me 3/2, so I have 2/3 y to the 3/2 from 1 to 1/2. 2 root 2 pi. I'll actually go ahead and pull out that 2/3, which makes this 4/3. And we're just dealing with y to the 3/2. So I have 1 to the 3/2 minus 1/2 to the 3/2. 1 to the 3/2 is just 1. And if we think about 1/2 to the 3/2, well, that would be the same as cubing 1/8. So 1/2 cubed is 1/8, and then we have the square root of that. So we need to figure out how to rationalize that. So just this piece right here, I'm going to do with some scratch work. That would be like the square root of 1 over the square root of 8, which is 1 over root 8. And that, of course, simplifies to 2 root 2. Multiplying by 1, root 2 over root 2 gives me root 2 over 4. So my final answer here I have 4 root 2 over 3 pi times 1 minus root 2 over 4. That represents the surface area of the shape created by revolving that arc, the right half of a parabola, about the y-axis. And if I do that, I kind of get a bowl or a cup shape. So we're finding this area of just the outside region.